Thanks for the introduction. My name is Jesus Antonio. I'm very happy to be here today talking about wearable-based long sounds and impedance pneumography. And I want to start with this question, which I think I don't need to motivate too much because you probably have a good idea of the answer. But why wearable-based respiratory monitoring? We will look at some numbers from the WHO to get an idea. We see that respiratory diseases account for basically 3 of the 10 leading causes of death globally. And that does not even include COVID-19, which we know for sure that it's going to be among those 10. So those are going to lead to structural changes to the lungs and airways, and we would like to interrogate or assess those in a practical manner. And yet what we have is the gold standard is highly specialized and inconvenient, and in many cases very subjective. So we have like the chest x-ray, the traditional auscultation with the stethoscope, and we have the spirometer for airflow measurement. So that tells us that we need better tools for assessing the respiratory health, and we would like to do that in a wearable form factor. Yes, so digital auscultation is definitely a convenient and non-invasive alternative, particularly because it provides high-quality audio recordings. And I say particularly because the ability of recording the sounds enables computerized long sounds analysis, and we can do data set generation, model prediction with those data sets in various conditions that go beyond the research settings, right? But one of those, 2 of the main disadvantages of digital auscultation is that it cannot provide continuous recordings, right? So we cannot practically hold the stethoscope, even when it looks nice, we cannot practically hold it for more than 2 minutes, perhaps. And then on top of that, and most importantly, perhaps the acoustics only are not sufficient. So what I mean by that is that the recordings lack the context of the respiratory activity that produces those very same sounds. And I'm referring specifically to the breathing phase, so the inspiration and expiration. And we know from the literature that, for example, normal long sounds are strongly inspiratory, but the opposite can actually be pathological. So that could be, for instance, in bronchial breathing in ARDS, for instance. And then the breathing depth or airflow, which we know also from long sounds literature that the sounds are directly proportional to the airflow. And actually a clinician uses that context when they're listening to the sounds to kind of guide what they're listening to and determine whether the sounds that they are listening to are sufficiently loud or abnormally weak in the specific breath phase. But only with acoustics can we really tell from a given recording if the sounds are reduced or absent if we don't have any information of the respiratory context. And that means that we cannot really assess the long sounds intensity, which is one of the critical components of auscultation beyond classifying the type of sound. And it's important because it relates to sound transmission and generation. And we see that on the right where air comes in, goes through the entire airways and parenchyma, reaches the chest wall where the stethoscope is, and that's the sound that we record. But that sound is a function of many things. And one of those is airflow. And we know from prior work that if we know airflow, then we can know if the person is breathing or not, we can know the phases. But interestingly, we can calculate the flow sound dependency and actually correct for it in post hoc processing. And using those corrected sounds, which I call standardized sounds, enables us to assess the transmission properties of the chest, kind of independent of the airflow that generated them. And yet, airflow requires benchtop equipment, so we're not really there yet. What we propose is a system that we recently developed in our lab, which is a wearable alternative for respiratory acoustics and airflow measurement. That is a multimodal system. It has 2 separate boards that simultaneously sample, and it measures impedance pneumography, so the bioimpedance, the transthoracic bioimpedance of the chest, and that is a surrogate of volume and also flow, and that has been shown a lot in prior work. It also has accelerometry, so an IMU for chest wall kinematics, and importantly, has multi-channel acoustics specifically for contact microphones that it simultaneously samples. And then here's a view of the system. This system, we have validated it in hospital settings in patients with heart failure. And that's the recording that you see on the right is from a patient with heart failure, where we observe the respiratory reference on top that's enabling us to determine that these are particularly inspiratory crackles, which are particularly interesting for heart failure patients. And we also demonstrated that we can use the breathing phase context for long sound lung sound classification recently. Okay, so we have the system, and we ask ourselves, can we use wearable-based lung sounds and impedance tomography to quantify and standardize the sounds? And here's our approach. We measured with our system simultaneously with a ground truth spirometer. We measured specifically the IP in the tetrapolar configuration, so one pair for injecting current, one pair for measuring voltage, from which the impedance is derived. We computed the airflow signal, which is the first derivative of the IP plus the smoothing. And then we have the 3 of the 4 channels were used to, well, simultaneously sampled, and we extracted amplitude features from the inspiratory part, which is the part that has been studied the most. And then we did this while patients were, well, these were not patients, these are young healthy volunteers, 10 of them were doing a breathing protocol to modulate the breathing depth and hence the airflow too, from shallow to deep. And then finally, we took that information, we calibrated the IP with the spirometer, and we correlated the lung sounds amplitudes for all 3 channels against the calibrated IP signals, so impedance tomography. And then we did that for the 3 channels, and then we also evaluated the effectiveness of a flow correction method to get rid of that flow sound dependency. I don't think I will have time to go in depth into the signal processing, but briefly, we have the spirometer and the impedance tomography signals. They go through pre-processing, which is resampling and bandpass filtering, and then we extract the phases from the impedance tomography to detect what's inspiration and what's expiration. We do the airflow calculation, and then also the amplitudes of the airflow, so peak inspiratory flow, peak expiratory flow, and then we use those to calibrate the IP signal. And then to calculate the intensities, the lung sound intensities, we then take the 3 channels, and then again, we pre-process them, resampling and bandpass filtering, and then we fuse the inspiratory onsets, as I mentioned before. That's the part that we're interested in this work. And we compute the peak-to-peak amplitude, which is fundamentally the average of n 25 milliseconds windows that in the inspiratory part. And I call that the AN3, which is the non-corrected one, or just the normal one. And this 25 millisecond window is from prior work. And then for the correction one, we now take the calibrated airflow. We use it, as an input now, and then we do basically the same procedure. But now what we're doing is only using the windows that are above a certain flow threshold, and that's why below that threshold the sounds are not audible, so it's below the noise floor. And then we basically divide every single window amplitude by the average flow in that window. And here are some of the results. This is the IP-derived airflow correlations to a spirometer, where we show that we found very good agreement and very good correlations. So we have an R-square. This is the average of the subject specific, so there's a plus minus. It's like R-square of 0.96. And then the Bland-Ullmann agreement also showed very strong correlation, strong agreement. And here's perhaps the most important figure of the paper, which is the demonstration of the flow sound dependency quantification using our signals. And then we see that on the top row, and then on the bottom row, what we see is the corrected one. So using the flow correction method. And in the columns, what we have are the channels, so the 3 channels that we simultaneously sampled. And what these plots are telling us is that in the one on top, we see a positive and significant association between the peak amplitude and the peak inspiratory flow, the calibrated one, in the range of 0.5 to 2.8 liters per second. And in the one below, we see that association is not significant anymore. So we have been able to successfully kind of cancel that dependency of intensity with peak inspiratory flow. And what that means is that we can now use these sounds, these corrected sounds, as a marker of sound transmission, rather than including both generation and transmission. And that's important because we could, for example, use this in a patient population where we know that there's structural changes that are progressing over time. So with emphysema, for instance, there is a death of the lung tissues. or destruction of lung tissues. We could have like we could have pleural effusions, or there's accumulation of fluid in the pleural space, or pulmonary edema. In those cases, we expect changes to the intensity that are not due to flow. So we could use a system like this for a technology like this for that purpose. Now, of course, because this is a feasibility study, so there are several limitations, and perhaps the most important one is the need for calibration. So I've been saying that we need wearable systems. We would like to do this wearable. Calibration is not suitable for such a wearable system. So we're working on that. And actually, this morning, my colleague in Berkebile, he presented some of our recent work on developing models that leverage the multimodal signals that we have, fuse them in a way that enable more like subject and posture specific calibration procedures to volume and hence to flow as well. Of course, we're looking forward to validate this technique in larger airflow rates and different postures. And of course, uncontrolled breathing will be studied as well. And then correlation to clinical state, it would be important to also, for instance, use ground truth of like X-ray to know when there's fluid, and then track that progression with markers like this to see if it tracks them. We will be looking forward to include those standardized amplitude features to predictive models of disease based on acoustics, which we have recently published a paper where we demonstrate that having the breathing phase context with our system is better than using just cycle by cycle in a long sound classification task. And we will certainly look to optimizing the system and miniaturizing it to have a more practical, more wearable system. And with that, I conclude. Thank you so much.